In the previous lectures, we had did a lot of analysis where a plant was of the form 1 over S over 2. We saw what happens when the controller was just the number 5, or now we know this is a proportional controller with the proportionality constant to be equal to 5. We saw various effects of uh, this controller on the step response and also the ability to reject disturbances. What we did later on was add an integrator or divide the 5 by S, and the controller now became 5 over S. And if I look at disturbance of unit step, of course this will translate to the result will hold for any disturbance of any magnitude. So in this case, it turns out that the steady state effect of that y because of d in the steady state becomes 0. Okay, and what we were also interested in is what happens to the error term. So if I look at the effect of the disturbance to the error, so E of S over D of S can be easily computed to be the negative of Y of S over D of S. So if Y at steady state is equal to 0 because of disturbance, the E at steady state will also be equal to 0 because of the disturbance. And we just named this as the integral control action largely because of the S sitting in the denominator. Hello and welcome to this lecture number 3 of week 5. We will continue our discussion on controllers. In particular, we will talk about a proportional plus integral plus derivative controllers. Okay, so what is this action of integral control? The feedback signal is linearly proportional now. So if I just look at the block now, suppose the integral control sits here. I have the reference. Here is the error coming because of the output. Here I have my plant. Okay, so the feedback control signal, now this is the control to the plant. G is my plant, is linearly proportional now to the integral of the system error. So I can write this as U of t is some ki, some term ki times the integral of the error. So the control signal at each instant of time is a summation of all past values of the tracking error. And of course, I know how I can really write it nicely now in the Laplacian domain. It just turns out to be a beautiful structure of ki over s. Relate this to 5 over s. So, okay, note that the controller has infinite gain at DC. That is when s equal to 0, the gain of the controller becomes infinite. So largely I will have again my uh, topics of discussion here would be to look at steady state errors, to look at the effect of disturbance and so on, and also the transient response, and see how different controllers sitting here have an effect on the output effect on the output, effect on the steady state error, and also the ability to reject disturbance. Okay, so when I say that the control signal at each instant of time is a summation of all past values of the error, so I'm just computing now the area. So U of t will just be the summation of kind of all of this. Okay, this is nice. So recall that for a closed loop system, the tracking error is the error due to the reference, error due to the disturbance, and error also because of the noise. Okay, assume now that I do not have any disturbance and noise term. That ns equal to 0 and ds equal to 0. The tracking error because of the reference becomes just this. So this we also call this as 1 over 1 plus L times R of S. Okay, now if G of C is of the form Ki over S, I do a little bit of math here, and the error for a unit step input now becomes 1 over S plus Ki times Cs. And assuming, so what happens at this steady state? I apply the final value theorem, and it turns out that the error always becomes zero, irrespective also of the value of Ki. Of course, here I'm assuming that the denominator, that this is a stable transfer function. Okay, similarly, I can do a bunch of things here. So I have again, if I look at the closed loop system. So here I have the error E of S. The important signal here is U of S, which actually tells the plant what to do in terms of meeting the desired performance specifications. So let me look at two terms here. Y of S, so this is my closed loop transfer function. This I know. Another signal is what happens from the reference to the input. Okay, so this is a transfer function from the reference to the input. Now I'm dealing here with a PI, with just an integral control with Rs equal to 1 over S. I have something like this, and Us becomes something like this. Okay, why am I doing this? So if I use the final value theorem, I know that because of the integral control action, again assuming stability, y at infinity is equal to 1, and u at infinity now becomes simply the inverse of g of 0. The steady state control is a constant and is equal to the inverse of the DC gain of the plant. Okay, I'll do this, we'll just stick to this example and understand what this means. So I have, uh, so uh, y of s over r of s was gc over 1 plus g times gc. Similarly, the transfer function from u to r was gc times 1 plus g gc. So I had the plant of the form g was 1 over s plus 2. gc is 5 over s. Let's look at what is y of s for a unit step. So this will become uh, 5 over s plus 2 over 5 over s plus 2. So this becomes 5 over s square plus 2s plus 5 and times the step. So y at infinity, using the final value theorem, you can easily check that this becomes 1. Okay, let us look at what happens to u at infinity. So u of s is now gc is 5 over s over 1 plus 5 s plus 2 1 over s. So this becomes a 5 here, s square plus 2s plus 5. I'll have a s plus 2 here and a 1 over s. Okay, so u at infinity now becomes what? So I'm looking at uh, again limit s going to 0, s times u of s. So this will be 5, this will become 2. Okay, now what is this 2? Look at what is my plant. G at 0 is 1 over 2. U at infinity is now 2. So what did we claim here? u at infinity is G0 with the inverse. So for the system to have a zero steady state error input at steady state, we need a certain input to hold the system at the value of 1. So there is some input also. Just like if I just want to hold this at say this angle, I need some constant kind of force or something here to hold it at this value. Okay, so this is again nice. So the steady state control is a constant and is equal to the inverse DC gain of the plant. And this could be true for several other situations also. Okay, so the effect of disturbance. The output, okay, so I'm just doing all these things. So this we saw in the previous lecture, that y at infinity because of disturbance becomes 0, precisely what we were trying to do here. This is my y at infinity. Similarly, I can see that u at infinity now becomes a negative of 1. Okay, I'll skip these steps, but very similar steps to what we just did. Uh, okay, so the steady state error is 0. Okay, and the final value of the control cancels the disturbance exactly. Okay, so this is why this is the y because of due to the disturbance input. Okay, the y due to the disturbance input in the steady states becomes 0, which means there is no effect of disturbance on the output in the steady state, for which we need a input of -1 to cancel exactly the disturbance signal. The integral feedback, so the integral control results in 0 steady state output error, both in tracking and also in disturbance rejection, or tracking a step input. So again, we'll again come back to the example that we had of a thermal control system. So G of S was this nice structure. Same things I want to track a reference which looks like this. So it is initial slope and then settles down to a constant. Can we use integral control to see what happens to the steady state error? So I do all the math here, the characteristic equation. So this is my plant. The controller is of this form. The characteristic equation, or this is the denominator of the transfer function. So this one. Okay, so what happens for different ki values? We see that of course the error in the steady state goes to 0, which is nice because again after a while I'm tracking like a constant input. And what we see here is, well, there is some initial error between uh, the reference and the actual. So in the earlier case, we saw that this error was kind of deviating, right? Because it was a type 0 system which did not have the ability to track a unit ramp. Now this is a type 1 system. It tracks a ramp signal with some steady state error. So if this were to just be my reference signal with the integral control, I could only track it with some error. Okay, but however, after a while we are tracking a constant input, and we know that when the reference is a step, the integral control makes the system to be type 1, right? So you have a S here. This makes the system a type 1, and therefore it has the ability to track reference steps. Okay, so this is nice. Then we go to a derivative control. Okay, so before we go to the derivative control and see what, we'll just again stick to this example. So I have a plant again of the form 1 over s plus 2. I had 5 here, all in a closed loop. So the closed loop transfer function here becomes 5 over s plus 7, and the output y, because y of s while tracking a unit step in the steady state, so y at infinity will be 5 over 7. So this whatever 7 7, this will be 0.71 and so on, and the error at infinity will be some 0.28. It will just be a 1 minus 0.714 something. Okay, so there is some error, and then if I just look at I'm assuming I'm doing the math right here. So if I just look at the step response, this is my unit step. The system only can reach up till this point, resulting in a steady state error of 0.28. Okay, what happens when so earlier what we did, we had 5 over s. I do not know 5. I do not do 5 over s. Let's say I do 5 times s. Okay, 5 times s. So now my y of s becomes y of s by r of s is 5 of s plus 2. Okay, so that is a little better. This 5 of s plus 2 over 1 plus 5s s plus 2. So this gives me, so there is a 5s in the numerator. I have s plus 2 plus 5s. So this is 5s over 6s plus 2. Now the output, because of a unit step in this steady state, becomes, okay, so there is a limit s going to 0, s times all of this with 1 over s becomes 0. Okay, something strange is happening, that I just have, okay, it start with some arbitrary initial condition, and the output actually goes to 0, right? When I did nothing, I just added a 0, and something strange happened. The system, which now had a steady state error of zero point 0.2, was actually going to 0. So this is also called the blocking effect of a 0. Of a 0 at s equal to 0. Okay, and this is just the derivative component. Okay, so back to more analysis. So in the derivative control, so again, goal would be to all the time the goal would be to improve transient response, speed up the response, or slow down the response depending on my requirements on the overshoot and the settling time or the steady state error. And what we saw was the addition of an integrator or 1 over s term or ki over s helped a lot in one disturbance rejection, and also to reduce the steady state error with respect to a step input. Okay, so where does this come in? So I have again my reference. This comes through some feedback. There is a E. There is a d over dt coming in here with a constant. So what goes out is ke times e dot. Okay, and the control signal now is proportional to the rate of the system error. And the controller transfer function looks like this, kd times s, what we now had as 5 over s. Okay, so this is never used by itself, just for the reason, one of the reasons that we saw is it just has this blocking effect. Okay, so it is usually augmented by some proportional control. Okay, and then not only that, if I'm just looking at a constant error. Okay, so this is what was also happening, right? I had a constant error of 0.281. I added a derivative control. The derivative of a constant becomes 0, and therefore the overall output becomes 0. That's exactly what we saw in this analysis here. One of the explanation is that because the error is constant, the derivative of error is constant, and therefore there is no output. Okay, now of course the key feature we'll see a little later is that because it has the derivative of the error signal, it takes control action. It knows the slope, right? When I said E dot, I kind of know the slope, and when I know the slope, it means that I know the trend in the error signal. I know how fast the error is growing. So I know error may be slightly also in the future. Okay, when I say error, so then look at this. This is already I'm talking of a non-causal behavior. Okay, so uh, it can have anticipatory behavior. Of course, it's a non-causal system. You can see, right, five times s. So of course, all the time practitioners complain of derivative control is that it usually tends to amplify the noise. Noise by itself is unwanted. Amplification of noise is even worse. Okay, we'll come back to the comparison a little later. Okay, we now look at what we call as a proportional plus integral control. Like derivative control by itself kind of means nothing, and also integral control by itself may have few drawbacks. So we'll see what happens when I add a proportional term to the integral. So what happens is I'm just looking at k plus ki over s. Okay, and then I look at what is the response to what happens in the steady state. So the feedback signal now is proportional to, I have kp times e, ki times the integral of e with the controller transfer function of this form. So this combination allows for a faster response than just a pure integral control alone. What the integral term does is it raises the system by from maybe a type 0 to type 1, type 1 to type 2, and so on. And therefore, it can, if it's a type 1 system, it can reject constant bias system. So I can just write this as S times Kp plus Ki over S. So there is a pole at the origin, resulting in a type 1 system. The controller by itself is of type 1. Okay, so let's see the effects of disturbance, right? So if I take a slightly different plant, uh, say the plant now looks like I'll take a different color. Plant now looks like 1 over S JS plus B, and say to this plant now I have a constant controller, a proportional controller. Okay, okay, this is my standard configuration, this is my reference, error, output, and all that. And now I have a disturbance signal here. Let's say disturbance is of some magnitude T. Okay, so what is the effect of the output due to the disturbance? So this will be 1 over Js square plus Bs plus K, and when ds is 1 over T. Okay, so I also have E of S. So this is also the negative of E of S over D of S. Okay, so I do all the math. The steady state error now, because of the disturbance, becomes minus T over K. So it does not completely reject the disturbance, but it contributes to some small, maybe an offset or some value in the steady state. Okay, so does not completely reject disturbances. Of course, one solace we can take is that the disturbance does not make the system unstable. Okay, back to where we were. So this is the the steady state error because of a disturbance of this size with a proportional control. Of course, what we can do is increase k to make the errors small and smaller and smaller. But increasing k, so this is my omega n square, the natural frequency. This can make the system to be oscillatory in response, right? So increasing k and also increasing k can make the system also unstable. We will see very soon of why we are not always looking at arbitrarily increasing the gain k. Okay, now I do the same thing. Instead of just controller of the form k, I have now a proportional plus integral control. So I'm just writing this controller in the time constant form. It's still the same. Don't so nothing that uh, I'm committing any kind of a notational change. I'm just writing things in the time constant form. Okay, with this controller, my now becomes error to disturbance ratio becomes this, and because okay, I can just quickly compute that because of this s in the numerator, also because I'm increasing the type of the system by one, the steady state error because of disturbance becomes zero. So the proportional plus integral control eliminated the steady state error. This is not the error, this is the control. Okay. Now, of course, we have to always be careful that we first assume that the system is stable, right? We first need to check for stability. So this K and Ti must be chosen such that the poles are on the left half plane, or the roots of the characters equation must have negative real parts. Okay, so this is about the proportional plus integral control. We'll again come back to our example of the thermal control system. Okay, so everything remains still the same. The strategy is now to use a proportional plus integral control that minimizes the tracking error and reduces the steady state error to zero. Okay, so we saw only proportional control gave us some error. Only integral control, it did give us a zero steady state error. Let's see what happens when I use both of them in combination. Okay, so I see that of course the error goes to zero. Okay, not surprising. The error goes to zero, and what else do we see? Compared to the proportional controller, the PI control has zero steady state error. The proportional term helps achieve faster response by applying immediate correction to the proportional error, immediate correction proportional to the error. So this contrasts with the only integral control, which only accumulates the past errors, making them slower to system changes. So while both PI and I and purely integral control can eliminate steady state error, the proportional action in the PI helps to prevent an overly aggressive correction that can lead to oscillations, which can occur with an purely integral control due to its integral term. The P action reduces this error before it accumulates too much. You can see with the help of simulations. So not only that, the system took about 170 seconds to reach a stable state with purely integral control, while it took around 34 seconds to reach the steady state with a PI control. It's something here. Let's check what was happening earlier with the help of purely integral control. Okay, it took a very long time here, right? You see, somewhere here. Okay, so this is nice. You see why how P plus I has its own inherent advantages than compared with just a P. Okay, so we now come to a proportional plus derivative control. So it just takes the form of U is the again here I'm talking of U of t is the input to the controller, is Kp plus Kd times E dot of t. There should be a E of t here. Okay, so which means that my US over ES now takes this form. So a PD control now adds a zero to the loop transfer function. And we saw in one of the previous lecture, what is the effect of adding a zero to the closed loop transfer function, its effect on the transient response and so on. The derivative term acts on the rate of the error signal, this one or this one. The output now is proportional to the rate of this error signal. And we said that the derivative term anticipates a large overshoot because it knows how fast the error is increasing because of the information on E dot. So, and when the rate of change of error is high, it takes an appropriate control action. The effect can be noticed also in improved damping of the system. Okay, a structure would now therefore look like this in the standard control architecture. So we start with few examples. Again, I have the standard plant with 1 over j square. It's just a rotational element with some moment of inertia. So I just have 1 over j square. If I just have a proportional element, what do we see is that the closed loop transfer function becomes k over j square by 1 plus k over j square. This is k over j square plus k, which means I now have roots at plus minus square root of k over j. So I just have purely imaginary roots. Okay, this doesn't help, right? So maybe I just keeping on increasing the gain will just move my roots only away from the x-axis, but they'll still be on the imaginary axis all the time. Okay, so with the proportional controller, with this plant, only a proportional controller, I just end up with a purely oscillatory system. But I just don't want oscillations. I want the oscillations to be damped. Now I choose a controller of the form P plus T. So choosing a controller of this form is nice in a way that, okay, so I see that Y, this is the output of the controller, also the input to the plant. You can also call this as U of S, is now GC times E of S, and of all this, so the output of the controller, which is also to the input to the plant, is KE plus KTD times E dot. So the derivative term again acts on the rate of change of the error signal. The output is again proportional to the rate of change of the error signal, the anticipatory behavior, and so on. Okay, so now the closed loop system now takes this form. So what was originally in the denominator only js square plus k, which was only oscillatory response because of roots only on the imaginary axis, now has a term here. What does this term denote? This term denotes to zeta, omega, and s. Here the zeta was 0. So adding a k 1 plus TDS adds some damping term here. And this system by itself for all positive values of k, td, and j is stable. System now changed from a purely oscillatory system to a system with damping. And note that this damping term in the characteristic equation or in the denominator of the transfer function is due to the derivative control. This also means that I can choose a proportional plus derivative control to shape the system's damping. I can choose appropriately by choosing the values of k and td. I can shape the system's damping, and the damping is related to the peak overshoot and the settling time. Right? Thus, I can say now that the PD control by itself can be used to improve transient behavior. You may want a faster response, a different zeta for that, zeta very small. I want a lesser overshoot, increase the zeta by a bit, and so on. Okay, so this brings us to the confluence of all of these controllers, the proportional control, the integral control, and the derivative control, for which the transfer function looks like this. Okay, so it kind of adds a zero at the origin. So if I and it also, sorry, it adds a pole at the origin, increases the system by from type 0 to type 1, type 1 to type 2, and therefore the ability to track certain signals. Okay, and with this we can see by appropriate choice of Kp, Ki, and Kd, I can shape both my transient and steady state response. And of course, the system has perfect tracking of step signals because of the integral control action. And the system also rejects constant disturbance inputs. Okay, so this is how the structure of it looks like. We'll start off with some very basic plant. So start off with a plant of sorry. Start off with a plant which looks like this. Okay, S square minus P. So far we have just been looking at stable plants, right? Now I have an unstable plant. S equal to plus minus square root P. So I have a root at P and a root at minus P. This is the unstable part because I want all the poles to be in the left half plane. If I just add a proportional controller, the y of S now becomes something like this. Okay, you can put a R of S also. So what this shows is that what are the roots are now decided by this number S square equal to B minus Kp. So if Kp is larger than B or smaller, so so I want this uh, minus B plus Kp to be this should not be positive. This should be negative, right? Uh, no, this should be positive for the roots to be imaginary. Okay, so minus B. So if I have a Kp which is greater than B, then this quantity becomes positive. Say some positive quantity, I call it P, which means S square will be equal to negative P, and I will have kind of imaginary poles. So an unstable system with a proportional controller can at best become marginally stable. Of course, now I know marginally stable. I was looking at the next step of what to do with this. I had the systems which were 1 over j s square in the open loop became 1 over j s square plus k in the closed loop. We just had imaginary poles. What do I do to damp the oscillations? Now I add a derivative controller. So S square minus B, start off now with this controller makes it, keeps it, pulls the pole towards the imaginary axis. The derivative component now adds damping to the system. So I am introducing a zeta here. So for positive KD, positive KB, and KP, this still holds KP greater than B, system is stable and I can arbitrarily place the poles. When I say arbitrarily place the poles, I can shape what is the zeta, what is the omega n, and thus achieve desired transient stability specifications. Okay, but what happens is that now I see that the system has some steady state error because of some steady state error for a step reference. Okay, and how do I eliminate the steady state error? I need to have the system to be of type 1 for it to track a step. I just add an integral component. Okay, so this will make the steady state error of the system to go to 0. Okay, so the limit y in the steady state becomes 1, and now we have perfect tracking. We started off with an unstable system. We made it marginally stable with just a proportional control, added derivative control to damp the oscillations. There is a steady state error, no problem, just add an integral control. So to conclude, we have seen the basics of integral control, derivative control, and also P plus I, P plus D, and overall P plus I plus D, of how each of them has their own contribution in systems performance. The derivative control looks at the transient specifications. Integral control also looks at the steady state specifications. Proportional control has its own role in speeding up the response and so on. In the next lecture, we will see few practical aspects of PID control. Thank you.